Welcome to our heat engine video. In this video, we will discuss the overall design process of our engine, the expected performance of our heat engine, and the actual performance of our engine, which was 0.28 joules, and reasons for deviation between the expected and actual performance. Throughout this project, we learned about PV diagrams, how to store potential energy, and the importance of technical knowledge and proficiency, and how both are needed for best performance.
For the design of our heat engine, the goal was to work off of a specific group's design and try to make improvements upon it to increase the total energy stored. We planned on using a one-way bearing along with a rack and pinion mechanism to lift to a higher height. By using the expansion work of the piston, this would push a lever, which would then push our rack upwards. The one-way bearing would prevent the rack from falling when the piston would lower from the metal canister being cooled. We had additional redundancy planned into our system to use a tooth to hold up the rack in case the rack and pinion / one-way bearing failed. However, due to construction issues, time constraints, and overzealous hot gluing, that redundancy was never added successfully into the system.
Since the expansion and compression of the piston is a cyclic process, the PV diagram should indicate the cycle by starting and ending in the same state. The first process would be isochoric expansion, since the volume is held constant. The metal cylinder, which starts in the cold bath, therefore a cold temperature, is moved into the hot bath. As the temperature of the metal cylinder increases, the pressure inside the cylinder increases as well. When this pressure is able to lift up the piston, and the pressure is able to counteract the weight of the piston and the surrounding atmosphere, this is where the process stops. Using pressure equals force over area, we can then use Newton's second law and rearrange the sum of forces equation, which is weight minus pressure times area equals 0, or in other words, the force experienced by the piston due to the pressure equals its weight. Using this, we can then derive that the second pressure at state 2 is the weight of the piston divided by the area of the piston plus the initial pressure. In this case, we will assume that the acceleration of the piston is 0, since testing with the piston and metal cylinder indicated a very steady rate of rising visually. The second process is isobaric expansion, since the pressure of the system is now held constant. This is due to the force from the pressure and the weight of the piston are now equal, and the piston will move steadily upwards until it gets to the top of the chamber, therefore at the system's max volume. The volume at this state can be determined if we treat air as an ideal gas and use the ideal gas law, which is m times r times the temperature of the hot bath divided by the pressure of the state 2 equals volume. The third process would be isochoric compression, since once the piston has reached its greatest volume, the only way that the piston will fall back down is if the pressure changes, which can be induced by changing the temperature of the air. At this state, the metal cylinder will be moved from the hot bath to the cold bath, which will cause the temperature of the system to drop, since heat will move from the hotter object to the cooler object spontaneously. At this part of the cycle, the piston will fall, causing its handle to also fall. However, if we implement the design correctly, the one-way bearing should stop this movement from affecting the storage of the potential energy and keep the rack and the weight at its current height. While the temperature of the air decreases, so does the pressure, since the two properties are directly related. The final process of this cycle is isobaric compression, since the pressure of the air will return to its original pressure, and it will remain at this initial pressure during the collapse of the piston until it's bottomed out at its original volume.
For the expected work of our heat engine, we assumed that the work done by the piston per cycle would be converted directly into potential energy. However, this was an idealization from the beginning, as work would also be used in the form of friction and air resistance. By using this idealization, as well as the equations that we gathered from the PV diagram to relate the pressure at state 2 to the pressure at state 1, we made additional assumptions such as the room and piston being at standard temperature and pressure, or 100 kPa and 25 degrees Celsius. The density of air being 1.184 kilograms per meters cubed, and the hot temperature to be 100 degrees Celsius and the cold temperature to be 0 degrees Celsius. We were able to use the ideal gas law to find the necessary pressure difference and the change in volume to calculate the work per cycle to be 0.73 joules per cycle.
Our heat engine was able to have a total of 0.28 joules, which is much less than the expected performance. This is partly due to the fact that we made an idealization to not include the effect of friction or air resistance in our calculations.
There were many reasons for deviations. For instance, while we did not calculate to include friction, the actual testing mechanism had noticeable friction in the pinion and rack mechanism, as well as with the rack and the walls of our mechanism. Additionally, the distance between the teeth of the rack were not ideal for our system. Previously, we had not thought to account for the teeth distance being important. However, upon review during lecture, we now understand that we should have calculated for the ideal distance between the teeth in order to ensure that all work from the piston could be gathered in our storage of potential energy mechanism. We also had construction problems, and not a surprise, another theft in B2. Our construction problems involved using the one-way bearing and securing it to an axle so it would not slip. This ultimately could not be fixed, so we had to hold the axle in place during testing, which was unfortunate.
That's fine. We'll just cap ourselves.
Some things that we could have done to improve our performance was to use acrylic instead of MDF for the rack and the walls of our mechanism, as this would have greatly reduced friction that exists in the system. Additionally, calculating the distance between the teeth would have greatly improved our ability to prevent our rack from falling back down, which would have increased our overall energy stored. Additionally, finding a better way to actually implement our one-way bearing on the axle would have created a more independently working system, which was the ultimate goal of the assignment.